We have Mike Stroia. He is employed with AZZ Incorporated, headquarters in Fort Worth, Texas.
From the bridge preservation point, I'm coming at it a different angle from industry, looking at how we can learn from preservation and apply it to future, and whether that's learning through education, studies, or other applications. From industry, we're looking at that, at least our company is looking at that, how to extend life. But preservation we recognize is extremely important for you folks in this room, and engineers, architects, and federal highway and states for sure. I'm coming at this from, again, a different angle. I don't have expertise in polypropylene fibers, but I found that the information in this report was very worthwhile for corrosion resistant reinforcement and the fibers. And it's based on a paper from Dr. Anil Pitnik at the University of Akron, my arch rival in Ohio, Akron University versus Kent State. Certainly, Ohio Department of Transportation funded the study with aid of Federal Highway. Dr. Pitnik, and I'm not going to read everything about Dr. Pitnik, but he's a great guy. Certainly, he's very involved at the university for over 20 years, and I'll hit some highlights there and take your time to read it if you'd like. He's still at the University of Akron and chairing their Department of Civil Engineering. 22 years since this study came out, said 20 years. He's the co-author of over 120 technical papers and lots of research in Ohio and outside the state as well. Is still teaching. He's done several courses on engineering, including reinforced and pre-stressed concrete design, FRP, reinforced concrete design, senior design, tall building design, steel design, etc. But Akron's a very good polymer research university, and they also have one of the two corrosion engineering schools where you can get a corrosion engineering degree from start to finish, them and Texas A&M. So a lot of resources at the university provide the content for the paper that was just on the previous page there, reduction of bridge cracking through alternative material usage. It's an extensive paper, 344 pages, a lot of data on, of course, the polypropylene fibers and different types of reinforcement. And I'll briefly go through what the survey talked about, or at least the study talked about, at Ohio, which is the second most bridges of all the states, over 26,000 bridges, routinely develops a lot of continuous span structural slab bridges. A lot of short, small span bridges, but tons and tons of them are creeks and streams and hills and valleys. But they're, of course, all to the ODOT Bridge Design Management Group and AASHTO requirements. But the decks that they surveyed had transverse cracks with greater than those predicted by AASHTO and NACI guidelines after being in service for less than 1 year. So they started looking at that and trying to look and see why and try to come up with alternatives, just kind of like I said. Learn from what they've done, try to make applications and why, and try to see how. So they're trying to do something a little bit different. So the addition of polypropylene fiber to the deck, and these are the results of the survey, had the potential to reduce the cracking, they thought, and the overall goal was to identify the materials and methods to reduce that. From the crack surveys of 30 bridges they picked, and they had actually over 90 available that they could do. They kind of limited to 30 in the different districts and found that 26 of them had more than the recommended crack widths of 007, 26 of the 30 in that first year. And they also found that what they were using, meaning the maximum crack width of 007 with the bridge cracks with epoxy coated bars, was probably unrealistic for what the goals they had set out to. So change the bar a little bit, but change the practices as well, because they still want to use epoxy and look at alternatives for that. But there maybe through this study they found that they could improve what they had. So the addition of fiber to the deck without any changes of the reinforcement details, which they're using epoxy, continuous span bridges was found to reduce a factor of 3 to 4. So pretty significant data, and it was plausible to reduce the crack widths in future bridge decks. So that was the survey of the report, but I took a section of that and kind of looked at it and found this part of it, said that very little research is done, at least what they were looking for. There's some research for sure, but very little been done to perform the use of corrosion-resistant bars as a means to reduce cracking or look at and see how it can assist. So they designed some experiments in this study, basically present the results. Just to take a step back, though, if you look at corrosion-resistant reinforcement and just reinforcement in general. You can see the tonnage over here, hard to see, but the blue is 2 years ago. The next is what the last year figured out to be, which was just under 9 million tons of reinforcement. Previous year was 85, which is a down year. There's typical trends, and the trends are always typically going up. There was a reduction, and that year, the fourth quarter of that year is when tariffs started to hit. So a lot of hesitation in buying and a lot of foreign material that was in that wasn't bought. So there was kind of a hesitation in the market. We probably would have settled out even without just the cost of reinforcement in general. So it settled in close to 9 million tons in any case. But to look at the whole corrosion resistant market of all that 9 million tons, only about 1 million tons of that is corrosion resistant. And that's every segment, not just DOT, but whether it's parking garages, healthcare, construction, that's the whole industry. So 15% galvanized, all these flex up and down, but dominantly epoxy is the biggest part of that slice. And just to keep that in mind when we go through for future statistics and what's out there and what performs. Next is a series of different experiments. There's a bunch in here that they applied to different methods and different slabs and different types of pull-out tests to reduce, to look at cracking. And there's always going to be a pounds over slip that they're measuring. I took about 3 of these, looked at them specifically for this report. Significant of the pull-out tests. So the pull-out tests provide a good indication of the performance of the corresponding corroded or uncorroded reinforcing structural concrete in bond strength, development and anchorage in structural concrete, moment strength of the beams and slabs, cracking potential of beams and slabs, fatigue loading of the beams and slabs, and impact loading on the concrete structures. So they're trying to simulate an environment in which, this is what it is in the real world. So they're cost-effective tests, and, they certainly have done these over time. You can see this particular test, this first set of tests, is a little 6x6x6 cube with the different types of reinforcements in there. Prism specimens under identical conditions for all types of the bars. These are pictures of the bars that were laid out prior to casting them, but you have continuous galvanized rebar, MMFX 9100, stainless steel at 2304 at a 60 KSI, uncoated, galvanized, traditionally hot dip galvanized, and epoxy coated, and they're all provided by industry partners from the University of Akron. This is a setup for the accelerated corrosion test. You can see tubs and the flooded with different percentages of chlorides, but the concrete with polypropylene fibers was 10 pounds per cubic yard, which is pretty aggressive. The specimens were subjected to corrosion and also not corrosion. So when you look at the how they determine the pull and the pounds, it's measured by putting this 6x6 slab and a press, and you can see a gauge on the bottom there, and that's how they determine the pounds pulled and the stress. The test in this first looking at it, we're going to look at it 4 different ways: with corrosion, without corrosion, with fiber, and without fiber. And then start to compare those in different groupings to see the separation, because it gets a little blurry at the beginning with the different types. Test result. You can see you want to be far left and high. So looking at this, you have a load of almost over 9,000 pounds where you're starting to separate from uncoated and epoxy. So that's hot dip galvanizing in the gold, stainless steel in the blue, MMFX, and continuous galvanized towards the top there. So this is with fiber and no corrosion. So pretty good results. You want to be, again, far left and high. So comparing that to the next, adding corrosion into it with fiber, you can still see a similar result where galvanized and stainless steel, MFX, and continuous are above uncoated and epoxy, but slightly lower and slightly more towards the right. So you go back and compare that to this. That's a little bit different. And now we're going into the area where no fiber and no corrosion. So no consideration of any fibers in this, but you still have a pretty good result in the pounds over slip. But they're all a little closer, except for The traditional hot dip galvanizing is closer to uncoated and epoxy versus the three stainless steel, MFX, and continuous galv are pretty rope tight, around 8,000 pounds and less than 0.02. Adding corrosion with no fiber, again, a little further separation, continuously galvanized MFX at the top, stainless steel moving a little bit over to the right, and you can see the results in the rest over top of that. Now, grouping these slightly different because those get a little blurry there. You can see what we're calling corrosion resistant, separation from epoxy. This is with fiber in corrosion. Again, a pretty good separation. No fiber and no corrosion, which is would be your standard bridge everywhere, basically without the additional fibers, is high and to the left for the three over top of epoxy. Corrosion, similar result, but a lot less load over the slip there. Just another couple groupings here over what's traditional Ohio. Again, a big separation. That was fiber with no corrosion, corrosion with fiber, and no fiber, no corrosion here, which would be the majority of what they're doing out there. So in theory, if they switch, they could get some advantages over what they have in slip. And same thing, no fiber with corrosion. To show the impact of fibers and how they help, this is where it kind of sets it off. Fibers are going to help in every single case here, and certainly in here you have continuous galv, where you have the bottom two are going to be without fiber, and the top two are. So it's a pretty big difference between the peaks of these. The higher left and the higher up the chart, the better. So the fibers definitely increased. You look at that with epoxy, it's still sliding over to the right, but it is higher. It's certainly helped, no doubt about it. Uncoated as well. So you look at the three examples and you're showing that fibers do definitely help those as well. Another grouping of tests called direct tension tests, and there was several different kinds of this direct tension tests were performed, again, similar in prism specimens with different types of reinforcing bars, same ones, and the test performed determined how well the reinforcing bars bonded to the surrounding concrete, and compare the crack widths and the distribution of crack widths. So it's not only about the distribution of crack widths, but how close they are together, but the number of them as well. So the data collected in this applied load, stress in the bar, crack widths, and crack spacing. So all important in how chlorides eventually are going to migrate to the surface of the rebar. Ultimately. So the average concrete strength was 4,800 PSI in the day of testing. There's a lot more data in the report, obviously. I'm just capturing some of the highlights. And they applied this load at every half of a kip. Bond strength development and anchorage in structural concrete and cracking potential of beams and slabs are what's important here. This is the layout of the test. You see a coupling nut at the end with a loading jack, jack post, and a load cell to determine what the actual pull-out strengths were. Test results. This little black dotted line is just a data point where they took 40 KSI and they said, we're going to put the data points on there and say this is where the numbers lie. It's not a huge significant number, but it's just a data point that they set out in there. Again, MFX and continuous galv separating from stainless and epoxy, but all upper left and higher than the epoxy. And this one was with fiber, corrosion resistant bars with fiber, and this one was without fiber. So again, a pretty significant difference between the two with fiber and without fiber. Pretty similar results. So this one, particularly the grouping's a little closer with the continuous stainless MMFX. So taking all into consideration, Ohio went forward with a bridge in Hinckley, Ohio, just about a little over a year. So they should have some pretty good results coming out on a year in service over this bridge in Hinckley, Ohio. It was just a simple 3-span bridge configuration, 24 to 30 foot to 24 foot with a deck thickness of 16 inches. And the bridge was designed with a cap and connection at the two pier cap locations, integral abutments at the ends. It's really kind of a pretty normal bridge in Ohio, nothing fancy, but lots and lots of them. Kind of just to wrap it up, really, you know, in my perspective, again, it's from the corrosion resistant, but fibers did show to reduce the cracking widths and number of cracks. And then certain types of corrosion resistant rebars show that they can reduce cracking by themselves with or without fibers natural. Thanks to Western Ridge for the opportunity. Take any questions when you have them.
So what I was curious is when you compared no corrosion, no fibers, and the failure mechanism would be the concrete failing, why would one perform so much better than the other? The concrete is what's failing. So why would one bar perform better than another?
That does go into some detail to answer the question, but it's a reaction of the reinforcement and how they work. And there's usually some type of initial corrosion in concrete because of the high pH, and there's a reaction to that. With uncoated bar, you're going to get a little bit of stress and cause some cracking from some of the epoxy. What's that? Oh, with no corrosion?
Yeah, so I mean, they were inside in a lab, right? So if
It's
the
probably
concrete's-
has to do with just the diameter of epoxy is it's going to be a thicker bar, thicker mill, so you're not going to get a lot of slip. So the other ones have no coating or very little coating, so your pull-out strengths has to do with your pull-out strengths, and it's a smaller, ends up being a smaller diameter. I think
okay.
that contributes
Thanks.
to it. That's my guess.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.